Thank you very much. Yeah, welcome everybody. I'm very happy to give this lecture series on higher property T. Okay, so to manage your expectations, the higher property T will come in the last 3 lectures. And in the first 2 lectures, we have to somehow set the stage, introduce some basic stuff. Also, I will define property T, but it will not be like a full introduction to property T. Certainly, you could give a whole course on just classical property T. I will just somehow focus on things that we will need later on for the higher property T. And if you have questions in the breaks, feel free to come up. I'm very happy to talk about the lecture course also outside the lecture.
Roma, will your lecture notes be available online?
Maybe. Haven't thought about it yet. I can think about it, yeah. All right, so basic notions. And basic notions will be about classical property T and later on cohomology. So first thing is we have to say what is Kazhdan's property T in the classical sense. A notion that Kazhdan introduced in the late 60s and which has an enormous impact in mathematics. Impact is not easy to see. If you've just for the first time see the definition, I don't think you can really estimate the impact this notion had. So, definition of T. So the definition is in terms of unitary representations, and let's say what a unitary representation is. Unitary representation of a group, usually discrete or locally compact, well, it's just a homomorphism from G to the unitary operators of a Hilbert space. So let's denote the representation usually by P or rho or sigma or something, and then the underlying Hilbert space HP, and these are the unitary group of this Hilbert space. And that's it if it's discrete, and if it's not discrete, then there is some continuity such that if you take matrix coefficients, so if you apply this operator to some vector v and w, then this is continuous. So for all v and w. And this is usually called the matrix coefficient. And then, if you have such a representation, we say that this representation has almost invariant vectors Please let me know if you can't read anything, if it's too small. It's hard to change the font size, I know, consistently, but I would try. So if for every epsilon and for every compact subset in my group, there is a unit vector such that it's almost invariant in the sense that if you apply some element in this K to this V and you measure how far is it from V, then it's at most epsilon. And V has norm 1 here.
Sorry, are we only considering real Hilbert space? In general, we consider complex.
Yeah. We consider complex Hilbert spaces as the default.
So the matrix coefficients are complex.
Oh, yeah. Somehow I was thinking of, yeah. No, you're completely right. Sorry. C. Thank you. And
this is for all G and K.
And this is for all G and K. Right. And then we call the invariant vectors these are just the vectors that are really fixed by everything. We denote them by h to the g. All right. And now we're already ready to say what property T is, classical property T. So if you have, it's a property of the group. So let me just write, instead of locally compact, second countable, let me just always abbreviate this with LCSC. Again, most of the time it will be Lie groups or discrete groups or maybe p-adic groups. So a group G has property T. If every unitary G representation with almost invariant vectors has actually an invariant vector. And OK, 0 is always an invariant vector. What I mean is, of course, a non-zero. Non-zero invariant vector. And so some rigidity property, if something is almost satisfied, then you actually, it's rigidly satisfied. All right. Now I see somehow the order of my notes is a bit random. Anyway. Right. So of course, when you introduce a property, you want to provide examples. We will provide examples. We will actually, in the course of the proof, not today, give a proof that a certain group has property T. But this is a property where it's much easier to give non-examples than examples, because every example is already a theorem. It's not just like a one-line example. And so we will first see non-examples. And to formulate that, let's look at a specific representation that you always have, which is the regular representation. Yeah.
What is the LCSC?
Locally compact second countable. So Why are we introducing this?
Yeah. Or already in the unitary representation, why are we asking?
Maybe have some patience for I mean, trust me that this notion has huge implications. But maybe let me first get a bit slowly into the subject. Okay, so regular representation usually would denote it by lambda g, and it's a representation. So if you have such a locally compact group, then you have always the Haar measure. Invariant measure on the locally compact group, and you can form this L2 space of L2 functions on G with respect to this Haar measure. And then there's a very natural representation that just does the following, that if you have an element G acting on such a function, well, how does it act? It acts in this way. And then with respect, or with the help of this representation, you can formulate another property that you might know, amenability. So G is amenable if this unitary representation, this regular representation, has almost invariant vectors. That gives you an interesting supply of representations that have invariant vectors. And somehow, I won't prove this in this generality, but if you take, for example, just R as an additive group, right, then it's very easy to see that the following set of L2 functions, so you have to choose the normalization correctly, and then you just take the characteristic function on the interval, on larger and larger intervals. And these functions become more and more invariant, because if you apply a group element in R, you just shift this characteristic function a little bit. It has a large overlap with this characteristic function, and that gives you the almost invariance of this sequence. So if K is some compact set in this additive group, then if you look at the norms of so this is a unit vector, then this goes to 0 for G in K. So you see now that if you have this regular representation, and suppose you had an invariant vector, strictly invariant vector, then it would be a constant function, right, the way it is set up. But the Haar measure of a non-compact group like R is infinite, and it's only finite if the group is compact. So you see, you cannot have an invariant vector, and so amenability is quite disjoint from property T, and the only intersection are in the discrete case, the finite groups, or in the topological case, the compact groups. Okay, so that's an immediate consequence that, so let me say, or let me write what I said, lambda G has invariant vectors only if G is compact, or finite again in the discrete case. And so the only groups that are both amenable and have property T are the compact ones. And now coming back to your question, I mean, without giving you, like I cannot go into depth, but that was actually one of the most spectacular applications of property T in the proof of Margulis' normal subgroup theorem, where you want to show that, and the technique that he somehow applied was, he wanted to show that a group is finite, and he showed that it's both amenable and has property T. So he had to show that a certain group is finite, and there was no a priori bound on the finiteness, on the size. So you just, and you couldn't bound it, so, but you had to show that it's finite. And then that's really a strategy that is applied to show by analytical means that it has both these properties. A little bit in the same spirit, that if you have a property T group, then it always has a finite abelianization. Same argument, basically. So if G has property T, or compact. So how do you show this? Well, suppose you have an epimorphism of your group onto an abelian group. Let's call it P. And then we can look at the regular representation of A, and we can compose it with P to get a unitary representation of G. So and now this regular representation of A, because A is abelian, has an abelian group is always amenable. It has almost invariant vectors. And if you compose it with P, it's obvious that it still has almost invariant vectors. So this representation has almost invariant vectors. And since it's a representation of G, it has invariant vectors by property T. Invariant under G, but this is a surjective map, so it has to be invariant. The original one, the lambda A, has to be invariant under all group elements in A, because this is surjective. And again, this means that this group A is a compact group or finite group in the discrete case. Right? And that already gives you many non-examples of Kazhdan Property T group. I mean, here you have many non-examples, but if you take, for example, a free group, which has an infinite, discrete free group, which has an infinite abelianization, then you see from this argument, it also is not property T.
So you've essentially shown that groups, quotients of groups with T have T.
Yeah, okay, that's one of the exercises, which is which is one of the warm-up exercises. Yeah, exactly. So there is an exercise about which operations of property T preserve property T or do not preserve property T. Yeah, that's right. Right, and so first substantial theorem about property T, which was already in the original paper by Kazhdan in the late 60s, is that, and that's somehow the main focus here, focus is on semi-simple Lie groups, and he proved that SLN R for R greater than 3 has property T. Right. And that's a non-trivial statement. This is a theorem which we will not prove right now. We will prove something in this. We will prove that SLN QP, similar statement for QP for the p-adics, has property T, but later in the course, and by very different means than just by this unitary representation technology. All right. So let me now switch gears a little bit and introduce something that will play a role later on in the course. It's a technical tool that we need, and this is ultra powers. So I do not assume that you know, I mean, I assume that you somehow heard what an ultrafilter is, but let me say what it is. Let omega be what's called a non-principal ultrafilter on the natural numbers. And there are some axioms that tell you what this means. And the only way I can remember the axioms somehow is to view it as a probability measure. So this means that this is a finitely additive. It's not a sigma additive. It's finitely additive 0, 1 valued probability measure on the natural numbers. And the non-principal means that finite sets don't affect the result. So it gives you just these 2 bits of information. It's something 0 or 1. And non-principal means that this has zero measure. Okay. So there is you can look it up. It's a construction using Zorn's lemma, that these things exist. They're not constructive, but they do exist. And the reason you want to have this as a technical tool is that these ultrafilters allow you to take limits of non-convergent bounded sequences. That's the main somehow benefit. Right. Of course, you could go to a convergent subsequence if you have a bounded sequence in R, but somehow what the ultrafilter does is it pre-selects you right at the beginning of whatever you want to do in a very consistent way, these subsequences. That's one way to think about it. And how does it go? So let's suppose we have a sequence of real numbers. And it's bounded, so let's say it's in the interval from 0 to 1, right? And we want to say, what is this omega limit, this ultra limit of this sequence? How do you define it? Well, you subdivide the interval, and then if the measure of the indices n such that xn is in the left half is 0, then you would say, okay, the limit should be here in that half. So if that is 0, this has to be 1. It should be here. So in the next step, you go do it again. And suppose that this is then this has to be 1. And now you subdivide again and again, and somehow this gives you the limit. In that way, you go to this limit. All right, so nothing too magical, but it's a very convenient tool not to have to choose subsequences in a somehow consistent way all the time. And you can somehow make this construction much more sophisticated and take limits of more complicated objects. You can actually take ultra limits and ultra powers of unitary representations. So this is the next thing. If we have a sequence of Hilbert spaces, so no representation yet, just a sequence of Hilbert spaces, then we can look at the bounded sequences, so to speak. So this is the L-infinity product of those Hilbert spaces. These are just all the sequences of vectors such that the norm stays bounded. Not uniformly, but each one is bounded. And then you define the ultra product with respect to such a non-principal ultra filter as follows. So the omega ultra product, and I will denote it by this sign, this symbol. It's a quotient of this L-infinity product. This doesn't go higher? Okay. Okay, and what's the equivalence relation? The equivalence relation is that you identify two such sequences if the difference of their norm converges to 0 in the omega sense. Okay. So in particular, somehow, yeah, all the null sequences are identified with 0. And this becomes actually, sorry? Put it down, yeah. And this becomes a Hilbert space, so it's not just becomes a Hilbert space. So you have to say, I mean, okay. There's like obvious addition and also scalar multiplication, but what's the scalar product? If you have two such sequences, then the scalar product, the omega scalar product, is just the limit of the scalar products of the individual guys. And this is bounded, so you can take the limit. And in the exercise, we'll play around a little bit with this notion and also with the question, why do you do it exactly like that and not in another way? So if you have not just a sequence of Hilbert spaces, but you have a sequence of representations. So if pi n, and let me denote it now like that, if Hn is the underlying Hilbert space of the representation pi n, is a sequence of unitary gamma representations, then this thing becomes also a gamma representation. By the diagonal action of gamma. And there's a reason I said gamma here and not G. And the reason is that if you have a discrete group, which I usually would denote by gamma, then there is no continuity condition in the definition of unitary representation. And actually, if you do this for locally compact groups, it will be never continuous in the sense that I wrote down. So there is a way to do ultra products of unitary representations of locally compact groups, but it's more involved somehow. You have to modify this construction here a little bit. And we won't need it. We can always, whenever we do this construction, we do it in the discrete setting. Right, and then finally, if all these representations are just the same, so if pi n is just one representation, rho, then we don't call it the ultra product, then I will call it the ultra power of this unitary representation. All right. Now, back to property T. We can express property T now in a, if you want, more sophisticated way using this construction. So here is lemma, which is actually also, there's not much to prove here, but it's will be an important observation for us. So gamma has property T if for every unitary representation the following holds. So if you have no invariant vectors, so for every unitary representation pi, if you have no invariant vectors in your representation, then also the ultra power. Did I say power and just wrote product? I don't know. I said power, okay. Ultra power. Should be different. Then the ultra power satisfies the same. So here's the ultra power of pi. And it has no invariant vectors either. And so why is that? It's just looking at the definition. I mean, what does it mean that we have something in here, in the invariance here? It means there's a unit vector in this ultra power such that and unit vector means that the omega limit of the norms of xn is 1, such that, so I'm not doing anything wrong, right? I cannot move this. Yeah, okay. just to check. such that so, but in particular, somehow my ultrafilter, right? It selected me a subsequence. I get a subsequence of vectors that are almost invariant, that constitutes an almost invariant vector. And then property T tells me, okay, if I have such almost invariant vector, then I have in my original representation invariant vector, which I don't have, right? So this cannot happen. By T, and this cannot happen. Okay, so somehow the invariant vectors in the ultra power, they somehow are just the almost invariant vectors in the original representation. All right, and actually that's a discrete group. It's a characterization. You could define it that way. Maybe you don't want to define it that way, but you could define it that way.
Omega is arbitrary in your definition.
My omega is what?
Is arbitrary. Like there's many ultrafilters, right?
It's I fix one.
Okay. Okay.
Okay. Once and for the whole week.
So for any omega, it's always a characterization, right? Or like if A holds for one, then A holds for all, right?
Yeah. Yeah. Okay. Yeah. Yeah. That's correct. All right. I think I have to work now. So let's see. Yeah.
Sorry, I don't understand much about this proof. So you showed that if gamma has property T, then that implication becomes the case, right?
Right.
What about the other way around?
So for the other way, so suppose you have an almost invariant vector. So you have again a sequence,
Yes.
which becomes more and more invariant of unit vectors.
Then one
And
can combine
the whole sequence would be one element in the ultra power, and would be an invariant vector then. Yeah, yeah. So it's
Same
probably
construction works.
same. Yeah, I could probably just if and only if it's the same argument. It's really a characterization for at least discrete groups now. All right. So you probably noticed, no, it's gone, yeah. But I had this theorem that SLNR for n at least 3 has property T, and I did not write SLNZ, I just wrote SLNR, and somehow that's the next thing that is important for property T, but it will also be important later on in the course that we somehow want to switch between a lattice and an ambient group. So let gamma be a lattice. And okay, so this means, let me just write it. I guess you know what I mean. Gamma is a discrete subgroup. So such that there's a, the most hands-on definition is such that there is a measurable fundamental domain of finite measure in G. So gamma fundamental domain for the translation action of gamma on G. With finite H measure. So mu is the H measure in G. And of course, if the fundamental domain is relatively compact, then it will be finite. So for example, a discrete group that is co-compact would do the job. And to pass property T, and then also later in the context of higher property T from the lattice to the ambient group and back, we need a construction that produces out of a gamma representation a unitary G representation. And this is unitary induction. And if you know somehow in group cohomology or group, just discrete group theory, you know a construction which is called co-induction. And that would be the L2 analog of that. Not induction, co-induction. But here it's just called unitary induction. So let's look at a unitary gamma representation. And gamma is now in this situation. And so we want to build the Hilbert space first of this induction to G. And the Hilbert space will be a space of functions from G to the underlying Hilbert space of that representation. And these will be measurable functions, and we'll also identify functions up to null sets. So I'm not sure I want to put this all in notation. Let's just say up to null sets. So up to measure 0, measurable. And the function has a certain equivariance property. So if I have an element in G and I multiply from the right with gamma inverse, then this is the same as gamma applied via the representation to Fg. All right. And, oh, there's something missing. The L2 condition is missing. What's the L2 condition? So we look at the norm of Fg, and we integrate over not G, but G mod gamma. And you see, because of this invariance or equivariance condition, the norm of gamma of G times gamma minus 1, so f of G gamma minus 1, this is unitary, so the norm stays unchanged if I apply pi gamma. So the norm really only depends on the coset class. And so it's well defined if I integrate over G mod gamma, which would be somehow the same as integrating over such a measurable fundamental domain. And this integral should be L2, so this should be finite. And this is actually a Hilbert space. Then you can also somehow, if you have two such functions, define the scalar product by the integral over the scalar product. So you get actually a Hilbert space. And G acts still on this Hilbert space. We still have one action left. Here we act on the somehow on the right entry. on the right of the entry, and we can also act via G on the left. So, and that gives us a G representation. So we obtain unitary G representation. And this will be my symbol for this representation, the induction, by following. So int gamma G pi. So what does an element G do to a function f? It gives me a new function here, and this will be the function. Okay, and this is somehow the unitary, called the unitary induction of pi. Okay, there are certainly some things to check, which I didn't, but this is the construction at least. Okay, right. And then there is this theorem that is also already in Kazhdan's paper, that somehow gamma has T if and only if G has T. Okay, so I will not prove this, but it takes a few lines to prove this fully. But so if you prove, for example, this direction, what you prove is that right, you want to prove that gamma has T, so you look at a unitary gamma representation with almost invariant vectors. And so what you prove in this, for this direction, is that if pi has almost invariant vectors, then the induction also has almost invariant vectors. And then you apply T here, and then, which is also not hard to see from this construction, then use that if you look at the G invariance, this is just the gamma invariance. So if you look at G invariant functions here, then because you still have these gamma equivariance conditions, so you look at constant functions if you look at G equivariant vectors in the unitary induction. So constant functions corresponding to a vector in HP, but because you still have this gamma condition, these are actually gamma invariants. So, so you use then property T for G to conclude this is non-zero, so this is non-zero. So, but okay, it takes a little bit of effort to actually prove that. But this is how you use the unitary induction. And then Kazhdan concluded, and yeah.
So the definition does it
Here.
work for any subgroup of G?
Oh yeah, yeah. You can.
I just know of like linear representation. Like
You can do this more generally for closed subgroups. Yeah.
for closed subgroups.
Yeah.
And so then, like here.
You probably have to twist with the Ragon-Nikodym. Okay. To make it unitary. Maybe you have to write it a bit. But there is a unitary induction, yeah, for closed subgroups as well.
Yeah, or let's say discrete. Then there's no.
If you have, yeah, the question is only if do you get, if you look at this, now you have an infinite measure here. The question is how much do you get actually, right, in the unitary induction. But you can certainly write it down, yeah.
Is the question where finite covolume is used?
Yeah, where finite, yeah.
Is it used in the definition
Definition,
or
or
in
is
the...
Yeah.
No, I mean, I don't use that the volume here is finite. I mean, I can just impose this as a condition, right? The only question is the fact that this is finite here gives you a certain richness. This thing is somehow rich enough. It's in a certain sense bigger than the original representation. And if you don't assume this for gamma, this might not be the case. So it might be a very small thing. But I mean, you can impose this condition and write it down.
It's just like in the proof, like I mean, somewhere we're using that it has finite covolumes.
Oh yeah, here you use it.
And I think it's when you show that, like I mean, that pi has almost invariant vectors.
Yes, that's correct. That's correct. Yeah, this is definitely not true. The statement for discrete subgroups. Yeah.
Yeah. Okay.
Without any condition.
Okay. Thank you.
Yeah. So right, or corollary maybe. So this is a lattice in SLNR, and it has property T. And of course, there's a much more general statement about lattices in simple Lie groups of higher rank. But this is, we just write it down now for this specific group. All right, so let's see. What's the time? I mean, I have 2 minutes on the official, but I think I started a few minutes late, right? Up to 21.
You started at 21 minutes.
Okay, very sharp. Okay, I mean, there would be somewhat a good break point now, but I disappoint you. I think I have enough stuff that I want to use this few minutes and come to the next section. At least start it. So much about classical property T for now. For higher property T, this will be generalized using cohomology of groups. There is no like hands-on definition just in terms of unitary representation. So we do need cohomology, and most importantly, group cohomology. So I hope I don't bore anybody. Well, I might bore somebody. I don't care about that, but I don't hope I bore everybody by reviewing somehow basic notions of group cohomology. I mean, one way to define it, the easiest way, but it's not the only characterization that we actually need later on, is via the bar resolution. But that's the immediate way to define what group cohomology is. And in this course, we're mostly looking at group cohomology of a group G, locally compact or discrete, with coefficients in a unitary representation. Not just trivial coefficients, which is maybe the most familiar, but actually unitary representations as coefficients. And it's sometimes indicated by a C that this is a continuous cohomology. It somehow takes the group topology into account. And it's defined as the cohomology of a complex, and the complex is called the bar resolution. So what is it, the bar resolution? It's a, yeah, let's write it like this. Sorry. So you have a differential, that's the differential in degree p. And it's the usual homogeneous differential and homogeneous bar resolution. So it does the following. Yes, C stands for continuous function. So these are continuous functions. So the topology is the topology of uniform convergence on compact sets in this thing, in this function space. And now we define a differential, and it maps F to another map on tuples, and it does probably a very familiar formula, does the following. It's an alternating sum of something where you skip one entry. So this means you skip that entry. Right. And this differential is also equivariant with respect to the diagonal actions. So this is with respect to the diagonal G action. Right? If you have a function, you can apply, you get a new function by somehow. Maybe I write it. So what's this function? By definition, it's this function. That's the group action, and this differential then descends also to the invariance. And this is then a complex, and you can take the cohomology of this complex, which is kernel divided by the differential, or the image of the differential of the preceding guy. And this is continuous cohomology. With coefficients in pi. Right, of course, it doesn't have to be a unitary representation. It's available in much more basically every topological G module gives you such a thing, but we will mostly apply it for unitary representations. So now there is something which is a quotient of this group cohomology, a very natural quotient, and this is, let's say, also part of the definition. This is called the reduced cohomology. And what you do there is
homology or cohomology? You said the cohomology, but you wrote like a homology.
Is the P down or up?
This goes up. The differential goes up.
Last line.
The last thing you wrote.
The new one.
The new one. Right.
Oh, yeah. I thought the problem is here. Yeah. Okay. Thanks. Yeah, the reduced cohomology is just the same definition, but you start from the observation that the image is not necessarily closed, right? So now you have this topology on the function space itself of uniform convergence, and it's not hard to check that the differentials are continuous. So the whole complex is a continuous, or is a topological chain complex, actually a chain complex of Fréchet spaces, but it's not so important now. But the differential in generally does not have a closed image. And so you can somehow just define the reduced cohomology by quotienting out the closure of the image. And this will be a quotient of the usual cohomology, and it will be called the reduced group cohomology with coefficients in pi.
You also want continuous?
And also, yeah, I will forget that for sure. But yeah, reduced continuous group cohomology with coefficients in pi. And somehow, if you have such a space and the image is not closed, and you divide it out, what you get is a non-Hausdorff space. So this cohomology, another way to say it is also that this cohomology is Hausdorff as a space with the somehow induced topology, quotient topology on these quotients, if the reduced is the same as the ordinary. Right? And so I will stop now. What we will discuss next time, we still need to have a little closer look at group cohomology. For the applications of higher property T, we need to understand well the relationship between central extensions and second cohomology. So we'll review this also next time, but then we will use our ultra power technique to somehow study the difference between those two. Okay, and I stop for now. Thanks.
Thank you very much. Are there any questions? Maybe there will be questions later. So let's thank the speaker again.